I think they changed up. Yeah. So we are recording. All right. So today we'll hear some more about the environment, in particular environmental education. And my co-host for today is John Rohraback. He is a forensic chemist here in our department. Weren't you also a student here too? Are you a graduate of Andrews, John?
I graduated in 1980 and was a student analyst in this lab at one.
1980. So yeah, you were a senior to me because I started, sorry, in 81.
Right.
Yeah.
Yeah, we missed,
Okay.
missed each other.
Yes, yes, yes. So you worked with Dr. Ford, who
Uh,
was,
he was already the dean of the college, so I missed him
okay, I see.
regrettably. He was a great teacher.
Oh, he absolutely was. All right, so John, it's your role to introduce our speaker today.
Okay, we're delighted to have Dr. Amy Cannon with us today. She is a co-founder and executive director of Beyond B9. It's a nonprofit dedicated to green chemistry education. She holds the world's first PhD in green chemistry from the University of Massachusetts, Boston, where she worked with Dr. John Warner, a founder in the field of green chemistry. And many of our students might remember that he was here just about a year ago on this same platform and had a wonderful presentation. Amy has industrial experience also working with the Gillette Company and Raman Haas, and was an assistant professor at the University of Massachusetts Lowell before founding Beyond Benign. Her work is aimed at empowering educators to integrate green chemistry into their teaching and practice, and to prepare scientists and citizens with green chemistry skills. So at this time, we'll turn the time over to Dr. Amy Cannon.
All right, thank you so much, John and Desmond, for inviting me and for the introduction. I'm really happy to be talking to you all today, and I'm glad that John went first. He is an outstanding speaker and super inspiring, and I'm glad you got to hear from him a little bit, so hopefully you remember some of those pieces from last year. But I'm going to talk to you about the education piece. Back in 2007, when I left the university, I was actually there with John Warner, and we had opportunity to leave and continue our work outside of the academic system. And John really works on the research and innovation piece. And my mission is to carry out the education piece. And I'm going to talk a little bit about that. And I'm going to start with sort of a grounding, just in case you didn't, if you didn't tune in for John's webinar, why green chemistry and why do I think green chemistry is so essential? As John mentioned, I did an industrial postdoc for Roman Haas Electronic Materials, and they actually became DuPont and then Dow, and they're now DuPont again with all the mergers and all of that. But what I was working on was I was in the electronic materials and optical electronics. And when I first came in, fresh out of a PhD with, a green chemistry PhD, I came into our research group meetings with a challenge to design some new optical electronics. Basically, these are waveguide materials, which are a planar fiber optic. So those really ancient telephones that are landlines, and you pick up the phone off that's attached to the wall, that's basically communicating information through light, a fiber optic. And this is a planar one, and it's basically I was designing the top layer of a touchscreen computer or a really ancient handheld PDA device. But touchscreen computers use some of this technology. Basically, you have a grid of light in one direction and the other direction. And when you touch your finger to that grid, it interrupts the light and it sends a signal so you know what to do next on the device. So as you can imagine for something like this, it's very technical in the design, right? So we had a particular design criteria that we were designing towards. We had to have a certain solubility because we were coating it onto a surface. We had to have certain thermal properties because computers get hot and we don't want them to get warped or misshapen over time. So it had to have a certain melting point and glass transition temperature. It also had to be pretty strong and robust. You're touching it day in and day out. It had to have some good strength to it, but some give to it as you're, touching the screen. So it had to have very specific mechanical properties. Refractive index, basically we're bending light along within a material and we want to keep it in that material. So it had to have a very specific refractive index. Surface tension, all kinds of things. And each time we would create a new material that we were testing for this application and other applications too. We would test them to this criteria. And if they were outside of the scope, we would go back in and redesign it to get closer to our design criteria. And what didn't come up in the group meetings until I got there, it was a little, I don't know, I was a little pesty in terms of when I came in. So what about toxicity? What about environmental impact for this material? What is the toxicity? What is the environmental impact of this material? And shouldn't we consider that as part of our design so that in the same way, if I were a chemist, and we do this all the time as chemists, as materials designers, as polymer scientists, you name it, we design in and out properties all the time. It's part of our superpower, really, as chemists and as molecular designers. If I had a crappy polymer, and that is the technical, if I had a crappy polymer for this application that actually did get warped and misshapen after a period, after getting hot, I would say, wow, the thermal properties are pretty bad. I have to go in and redesign them out. We do this all the time. Why not? Why can't we do that for toxicity? Why can't we do that for environmental impact? Shouldn't that be within our portfolio of how we think about designing new materials? And of course, it's a lot more than that, right? It's not just the endpoint, the end product for which we're designing towards, but we also have to think about where are we getting our raw materials from? How is this product made and from what? And then where does it go after, once this computer has seen the end of life? What happens after that? And hopefully it's a little bit more circular than this with many of our products. But there's a lot to consider here, right? So there's choice of raw materials, reagents, solvents, energy. Are there byproducts or co-products created in our process? End of life, all of these things, which are beautifully articulated in these 12 principles of green chemistry. And if you haven't learned about the 12 principles of green chemistry, there's some really great resources out there. This is actually a very short book, an accessible book that helps give a really great foundation in this. And if you look at these principles, I'm not going to go into the details. They do focus on product, how we're designing chemicals. They focus on the process or the raw materials and starting materials. They focus on the process, like how we think about using energy, what choices are we making to make our processes more efficient, and of course, end of life considerations. So it's a more holistic framework for thinking about how we design materials. And why did we get to this point in the first place? I'm going to frame it with this case study. If we think about refrigerants, I'm going to use this as a case study. The first generation of refrigerants, which were created for actual refrigerators, that was one of the first applications of these materials, were around the early 1900s. And the first generation of criteria was basically whatever worked for this process. We were scientists and product designers were looking to create something that could act like a refrigerator. And the materials, the chemicals that were used in those first generation were, if you look at some of these chemicals, they're highly flammable or highly toxic, mostly gases. And they were so toxic that if there was a pinhole leak in those refrigerators that were early on, they were known to leak out into a home and basically kill families overnight in their sleep. And, that was a very unfortunate result of high toxicity. Or if they were so flammable that if there was a spark, like someone's repairing it and there was a spark created, refrigerators were known to explode. And so there was clear and present dangers and hazards that needed to be considered, right? So what do we do as scientists? We go back to the drawing board. We go back to how are we thinking about? We're going to try to address that high toxicity and high flammability. And that's our focus within our design criteria. And so we're looking at something that has low toxicity and low flammability and is really stable. And when we design towards a particular endpoint, that is exactly what we get. And so that's what we got in this next generation of refrigerants, which are chlorofluorocarbons, CFCs, as you may know them. And you may know these chemicals too as doing some significant damage to our ozone layer. They catalytically destroy our ozone layer. And we discovered that this was around the 30s and 40s that these were invented, and we started to quickly, well, fairly quickly within the time frame, that these are quite persistent, and they remain persistent up into our ozone layer and then catalytically destroy it. So we're learning more, and we have to go back to the drawing board and redesign out these properties, which is what happened in this third generation criteria. And now, by using our molecular tweezers and plugging out those chlorines and replacing them with fluorines, I know that's now not how it was actually done, but by substituting that with our hydrofluorocarbons and removing those chlorines that do that catalytic destruction, we now have, through our updated new design criteria, materials that are basically zero in terms of the ozone depleting potential. That's ODP down there. But we've discovered that they have a new endpoint, global warming potential, that is quite high. And so now we're understanding even more. And you can think about this in terms of a historical context about how much we didn't know and the history of what we didn't know. But you could also make the argument we know a lot more now today. And so it gives us so much more ammunition in our portfolio to design products that have these reduced hazards. So the fourth generation, the next generation, is what we have today. These are HFOs. Again, if you look at the structure of this, it's incredibly interesting to me, that these materials, these new generation of refrigerants are now dropping. We still have zero on the ozone depleting potential, and the global warming potential has dropped significantly. And if you think about this in terms of like what we need to do to achieve sustainability on our planet, we can wish all we want for people not to use air conditioners, not to use refrigerators, but people are going to use, and in many cases, refrigerators, air conditioning, the uses of these refrigerants is life-saving, right? And it really has transformed the way we live, and in some cases, it's life-saving technologies. And so what chemistry can do, smart molecular design, what that can do is basically it removes human behavior out of the equation, right? And this is a chemistry solution to a challenge that only chemistry can do, right? The way that we actually think about and create products. So there is tremendous power in smart molecular design. And if you get into this space, you will be a superhero. I'm just telling you, because it's the moment that you think about how you're creating a new product. And of course, this is a quote from one of my favorite green chemists, as you know, John Warner. The moment that we start thinking about how we're designing a new chemical product, a material, whatever it may be, that's the most important. We're making decisions for how it's going to impact humans, either in the manufacturing or end of life. It's impacting all of these decisions right then when you're thinking about pen and paper and when you start to do those first reactions to test out your procedures. That is the most important time where, if we're considering this in that process, again, we're going to have huge impacts further on down the line. Another person said this pretty well. I think it was Spider-Man and lots of other people that were credited with great power comes great responsibility. So we do, as chemists, as molecular designers, we have tremendous power. And there's all kinds of great historical examples of this, from detergents, where again, this was in early 50s and 60s. These were the first detergents. And if you just look at the structure of this, it's very branched, right? It's highly branched structure. And these had really low biodegradation, and that literally, if you turned on a faucet back around that time, you would, see foam coming out. Not everywhere. I'm just saying there were cases of you seeing foam coming out because the detergents were just not breaking down in our waterways. And so this was actually a quick turnaround time for a redesign on this one. We, again, taking our molecular tweezers turn this into a linear structure, and now this has high biodegradation. And that was actually a fairly quickly addressed in the history of, understanding this structure and how it impacts something like toxicity or biodegradation. And it turns out that we know a lot about what structures can either increase resistance to biodegradation or decrease it. So this is a nice example of how we might learn as we're learning about structures, as we're learning about in organic chemistry course, we're learning about all these things. Structures matter. That if we have these within our molecular structures, we're going to have a more persistent product. So if we know this, and then there's also features that decrease the resistance to biodegradation that we can understand. This is a great Chem Reviews article by Bob Bothling, who was at the EPA. This gives us tremendous power in how we're thinking about if we want to design something that has high biodegradation, then we might want to avoid some of these structures. And we might be able to predict some of that. And there's a lot more on this too. If you wanted to dig deeper on this, there's some great resources here. So if we're thinking and we're talking about, all of the sustainability challenges that we face in our global society today, chemistry is central to addressing each one of these. It's either central to addressing each one of these, or if it's not central to how we find the solutions to this, these sustainable development goals should be embedded in how we practice chemistry. So it's either one of those, and in both. And if you pick any one of these, the statistics are just daunting, right? And these are huge challenges that we're up against. Things like clean water and the communities that are impacted by these types of things. It's just daunting. But if you think about the solutions for something like clean water, water purification, there's chemistry, there's engineering, there's material, all of this is embedded in the solutions. We need chemists inventing new membranes, new filters, all of these technologies. And it's not going to just be one, right, that solves the world's problems. It's going to be so we need all eyes and ears. And again, we need chemists to realize their role in actually solving these challenges. And again, these challenges are directly related and interrelated, right? And they're intertwined. So this is another one, zero hunger. And, these chemistry, sustainable agriculture, all of these things are intertwined, and we need better chemical solutions. And we also are finding that industry is looking for students, they're looking for scientists with these skills to help them solve these problems and to help them avoid the next problem that might be coming as well. These are some of the companies that support our work and some other work in the green chemistry education field. This is Jeffrey Woodford, one of our big partners at Nova Sigma. They want students with these skills, and there's so much evidence that sustainability is it's a skill that we're lacking many times in the workforce, but that employers are looking for that will give you a next level advantage within jobs. And I would argue that there's a growing demand for greener chemicals that's not going to go away. We're not going to look back and think, oh, wasn't it silly when we actually cared about humans and the environment? It's only going to go up, right? Because we know all the reasons why. And then there's some nice reports out there that these are good jobs. These are good jobs in the field of sustainability and green chemistry. So this is a Department of Labor link. And if anybody wants any of these resources, please just let me know. I'm happy to share. So that transitions to what we do at Beyond Benign. So what we all want, right? Hopefully you're all in agreement with me that we're looking to create more benign, safer, more environmentally friendly products and processes in support of a healthy planet, right? And that's kind of our ultimate goal. And that's our vision here at Beyond Benign. We envision a world where it almost doesn't matter what you buy off the shelf. what we use every day, that those molecular building blocks of products that we use every day are safe and healthy for humans and the environment. That's a big vision, and there's a long way to go to get there. But hey, we needed a big vision. And how do we get there? It's got to start with our education systems. It's got to start early. If this is not embedded in how we're teaching and practicing and in our education systems, we have a huge missed opportunity, because we're going to constantly be trying to reinvent, up here, and we're going to be dealing with things way after the fact. The other piece is that innovation piece. Oh, sorry. So that's our mission. Our mission is to really focus on education, and we do that through empowering educators. The other piece that's missing is the innovation piece. And a lot of that comes out of academia. It comes from history. It comes from different places. And I know John is a huge innovator, and I hope he shared some of his great innovations too. We need more solutions. We don't have all the answers, right? And so we need more people. We need more eyes. We need a more diverse set of eyes inventing solutions for this big vision. And so I'm not going to go through the history of our organization, but we started back in 2007. And much of our work has been focused on empowering educators to bring change to their institution. And now we're looking at really bringing and connecting a community, and really bringing a community practice together that just gets better. The more and more we work together, and the more and more we empower each other. And we're looking at supporting this growing community of practice, and actually having it become a community of transformation. Some of the results that we're looking for changes in perceptions and attitudes about what green chemistry is, about what, the confidence to teach these concepts. And some of those attitudes and belief systems are what is required to actually make changes, right? If you're not changing perceptions and attitudes and beliefs, then your behavior changes are not going to change. And so these are some of our annual community survey results. We just closed our last one, so I don't have our 2024. It's actually the academic year. So I've got a new set of data coming very soon, and we're finding we're finding some pretty good results from our community. I mean, for a community of transformation, or looking to support a community that changes their behavior, these are pretty good numbers. And I wanted to share a little bit about our tongue twister of a name in the context of what green chemistry is about. Beyond benign, that term is focused on that sort of trifecta of what green chemistry is about. It's not good enough for a green chemistry technology to be beneficial for humans and the environment, and to have that sustainability benefit. It also needs to have comparable or better economics and performance. Many times that's the case. Sometimes there's some leeway within that structure. But basically the point is, we want things that are going to be used and that are cost effective. Otherwise, they're not going to be successful in the marketplace. And that's kind of the foundation for which, all of our curriculum and all of our work is centered around this. So our work is focused along the education continuum, supporting, there's all kinds of opportunities for empowering students to think in sparking that interest in chemistry, and also getting involved. And so from K-12 to inspiring future chemists, there's statistics out there that if by 8th grade students don't have a positive view of science, they will not study it in college. So it's tremendously important to inspire those next generation of chemists. And then, not everyone's going to become a chemist, right? So there's also opportunities for educating consumers and citizens. To demystifying chemistry, making it less abstract and more concrete. How does this relate to our world, right? So there's all kinds of opportunities. And then to the undergrad and graduate school, we're starting to train and support the development of new skills, and train 21st century chemists and professionals. So we're focused across this continuum, so much of our work, and the way that we carry out our work is by working with educators. We invest in educators, we develop tools and resources where there's gaps, and we foster peer support networks. We find that teachers talking to teachers, faculty talking to faculty, students talking to students it's super valuable to have your group and to have your peers that support you along the way and along your journeys. And we do it through strategic partnerships. Not one person, not one organization can do this alone. We partner with all kinds of different organizations. I'll mention a couple. And we are looking to instill diversity, equity, belonging, and respect throughout all of our work as well, so that everyone feels that green chemistry is what they can do and they can identify with this community and feel like it's their own. And again, those are some of the things that we're looking to increase that I shared on that percentages slide too. That's what we're looking for. So a lot of our work is focusing on this educator journey. We're inspiring, getting someone like a spark, and we focus on educators, but we also find that students, undergraduate students, graduate students are also part of this educator journey as well. We find that there's a lot of activation with student groups, either undergraduate and graduate student groups, and they do a lot to inspire change at institutions and in communities. So even though I say educators, it's also included there. So along this journey, we do things like webinars, we participate in conferences, symposia. We have a regular meetup called Green Chemistry Connections and Observe, Wonder, Think. I'll mention those in a second. We then try to deepen people's engagements by resources, professional development and supporting institutions through education awards. I'll mention that too, and leadership. And then we're asking our leaders that have gone through this journey or that are at different parts of their journey to come back and help us and work alongside us to develop resources to advance the community. Because again, we do all of our work in partnership with educators. So along this first one, webinars, conferences, symposia, we hold a couple monthly meetups, the Green Chemistry Connections here on the left. This is a monthly meetup for anyone. We actually have a rotating time zone right now because we're working with some folks in Australia across the other side of the planet to try to get some different time zones because we do have a global community. All of these events are on GCTLC. You can find them under the events and you can sign up and get connected. Observe, Wonder, Think is a K-12 teacher focus, and that's designed around next generation science standards. If you're familiar with some of that language, it might look familiar. So these are just monthly meetups that give a chance for people to connect with each other, find their peers, ask questions, learn, and just touch points. So those are a couple. We also participate in all kinds of different conferences, but those are a couple that we run on the regular basis. We also do special webinars, like one that we just did last week. This is there's all kinds of requirements now for use of methylene chloride. You may have seen that, and there's some restrictions and reporting requirements now. Methylene chloride is a suspected carcinogen, and there's all kinds of resources out there for pointing people towards replacements and phasing this out of their academic systems. And because we're finding our industry partners are, they are not, they're also looking to eliminate the use of chlorinated solvents such as this. So this is a partnership with the Laboratory Safety Institute. You can actually find a whole collection of resources on the GCTLC, which I'm going to mention in just a bit what that is, but it's an open platform that you can join anytime. You're welcome. So those sort of things are other kinds of things that we like to do to inspire people to think about how they might bring this into their day-to-day. Along that, as we're deepening our engagement, we have resources, we have professional development, and we have education awards to support educators and student leaders along this path to do more. So we have all kinds of open access resources. these are just a few that I'm highlighting. We have over 200 K-12 lesson plans and resources. This is a Plate to Planet, an elementary level module. Our JV Invent guide there is focused around invention. The one in the middle is, yeah, that's the invention one for biopolymers, so more renewable polymers, and that's around the middle school level. And then we have a high school book for how to integrate and think about this into a higher level chemistry course at the high school level. We have all kinds of resources. This is just a few to highlight. And then along the higher ed, we have these resource guides for organic chemistry course, lab course. We have an inorganic and Gen Chem guide, and then also an open resource that's called Toxicology for Chemists. So that, you know, as I was talking at the beginning, more about how structure impacts function like biodegradation. This is a full course. There's full course load of materials in there. And there's also little tidbits too that you can start dropping into your lectures and things like that to think about and empowering students to understand more about toxicity, hazards, and how that might make us stronger molecular designers. And again, so this is just a few. We're approaching about 300 resources on the GCTLC that just launched. And this GCTLC that I just keep mentioning is a new platform. We're coming up to our 1-year anniversary. We just launched it last October. And this is an initiative with the ACS, Green Chemistry Institute. And it's an open access platform with an open access resource hub. You can find all kinds of resources, search for them. We have a full resource database. We have forums and discussions where you can post questions, find your peers, find your network. Very soon, we have groups functionality coming, so it's not completely built out, but it's coming, where we're going to be able to create groups and do a lot more of that collaboration and mentoring. And then there's also a job board. If you're a student and you're listening, there's also a pretty robust job board. We've been getting some good jobs in there, so please, you know, sign up. And you also, if you sign up to this, you'll get added to a digest, and we usually post, you know, what's happening, what's the latest jobs, what's the latest in the forum. So you'd also get connected there. Okay, and so along the journey is also this leadership. So the leadership piece is what we hope everyone becomes, right? Like sort of that peer-to-peer mentoring, right? So the leaders and the mentors are the ones that work alongside us. All of our work is for and by educators. And so these resources that I mentioned were not created by us, you know, they were created alongside faculty that use this material and that have implemented these materials. And all of our programs were shaped by our faculty. So these types of resources were in partnership. And then we also tap into our network of educators, professionals, teachers to help us build something like this open access platform that I just mentioned. We've been working on that for the past 4 years, and this leadership committee has been essential in really helping us to bring together and create the GCTLC. And they represent high school teachers. We have a librarian on here that helps us with the information and data. We have industry professionals, faculty. There's a really great diverse set of folks that helped us create this. The last thing that I'm going to mention is our green chemistry commitment, which is really an institutional commitment to sort of demonstrate that leadership leadership and to deepen the engagement across a department across a chemistry department. So the green chemistry commitment is an institutional commitment, and I know commitment sometimes is a little scary, so I'll just say that. But I'll just jump over to this slide real quick. Even though it's a scary word, there's also this, if you look up the definition, there's also the state or instance of being obligated or emotionally impelled. And you say, I believe in sustainability. I believe of the transformative power of chemistry to address and solve problems. And so I'm going to commit, right? So it's in my opinion, it's not too scary of a word, but what it is basically an institutional commitment for chemistry departments to come together and say, we commit to continual improvement, to bringing green chemistry to our department. And there's a lot of different pathways. It's framed around some student learning objectives, which I'll mention briefly. This is sort of the history. I won't mention it too much, but oh, I have to update. Today we have 193 signers. This is an outdated slide. And even this slide, we cannot keep up with the number of signers. So this was, we have 193. We just got our first institution in Hawaii that just signed on. So they haven't been added to this. But we have 192 universities that have signed on to the green chemistry commitment, and it's been growing like crazy. Which is really exciting and inspiring. We have a strong, growing international audience and institutions here as well, which allows us to really understand and connect with the global community and learn from each other. It's been really inspiring to learn from other regions. I think we have about 22 countries represented. I may be slightly off on that. But on our green chemistry, on our website, you can also find a map, and that's under the green chemistry commitment, and you can see profiles of all the schools. The map is interactive, so you can click on the little icon. And so if you're wondering if there's anyone in your area, you can go right to that map, and you can you can connect directly with them. The green chemistry commitment is framed around these 4 student learning objectives. That upon graduation, students will have a working knowledge of the 12 principles of green chemistry. They will possess the ability to assess chemical products. So, we want this applied in the lab. And then they will have an understanding of the principles of toxicology. This is always one of those red flags, which is one of those reasons why we developed the open access toxicology resources. It makes us better designers. It makes us better chemists if we can understand more about the chemicals that we're working with and creating. And so that toxicology one is another piece. And then application, basically how this is applied in their professional capacity when students move on to careers. The exciting thing is that last year, the ACS, if you are an accredited institution, the American Chemical Society accredits undergraduate programs. And brand new in 2023 you can see some very familiar language here. Students would have a working knowledge of the 12 principles. This is a critical requirement in coursework now. And it's a marker of excellence for students to have the assess chemical products and processes and design greener alternatives when appropriate. There's also some really, it's a marker of excellence. I mean, how cool is that? I mean, green chemistry is excellence. It's not less than, it's excellence, absolutely. So if this is in your skill set, you're excellent. I'm just saying. You're also a superhero and you're excellent. So all of this is within, and there's a lot more materials within the ACS guidelines, but the other things, there's also some normal expectations for case studies, which we've got a lot more resources coming out in that space. But the commitment is a two-way commitment, right? So it's free and open and for institutions to join. And we are really just genuinely looking to advance the community as a whole. And we want to support the implementation of green chemistry across that education continuum. And so it's basically, here's what you get from us, here's what you get from what we get from you. We want to help support the community to practice more and more green chemistry. And we understand that there's different timelines and different strategies based on your own strengths within your department and all of these things in student interest. One of the things that we like to talk about is that if green chemistry commitment signing institutions are eligible for some mini grants to support curricular adaptations to include green chemistry. It could be also used for student groups or different groups to hold events to bring about awareness. Things we know that making some of these changes takes time and resources, and sometimes these little pots of funds can go a long way for really bringing something to your institution. So these are just some of our latest ones that were given out earlier in this year, and this is open now at the moment, and we have some more coming. It's basically like usually a rolling deadline. We usually have them open a couple times a year. And these are some of our most recent grant award winners. And there's a spectrum of what people are doing, from a student event that McGill and University of Toronto doing some student events to, some institutions putting together a departmental plan around how they're going to approach green chemistry, to others that are very specific to, hey, I need some time and resources to test out some of these greener labs. So there's a whole spectrum. And we celebrate the different paths that each institution takes. And we recognize that and we share that. So we know that each institution takes a very unique path. But what are the results? We also just closed our survey, so I don't have our 2023-2024 audit report, although it's coming very soon. But what we're finding is that our signers are increasing their green chemistry teaching and practice. They're reducing waste. They are finding opportunities to collaborate with other departments, other offices, and bring this to the broader context. It's really inspiring to see the work being done at so many of these institutions, because the chemistry education landscape is changing. There's a huge increase in green chemistry publications ever since that book was published in 1998. It's been, this only goes to 2018, probably needs updating as well. But it's on the rise, and it's going up. There's more journals, there's more publications, there's a lot more information out there now. And and these are, this is the map that you will see. The landscape is changing. We're hoping more and more of these little icons pop up across the globe. And we really need to have our systems and our educational systems transformed. And students today are looking for this. They're expecting this in our school systems, in our colleges and universities. They're expecting it from government. They're expecting us to be better. They're expecting us to teach more about sustainability, about what all of these things mean and how they can help contribute. They're expecting this from scientific societies, such as the ACS, and this is a Royal Society study. They want this, right? And it's the next generation, and it's the it's a movement, right? It's tremendously inspiring to me to think about what chemistry can do to contribute to sustainability. And I don't do this work alone. This is my team. We have, there's 11 of us. There's 2 pictures since I didn't get everybody in the first picture. But, so we have folks, and we are all a completely remote company. I'm located in Massachusetts. I've got folks in Canada. So 3 of our staff, Juliana, Nim, and Jonathan, are up in 3 different provinces in Canada. Monica's in the Upper Peninsula of Michigan. Natalie's in Vermont. And we have Michelle in New York. Chloe's in Pennsylvania. So we are all over the place. And we're actually growing at the moment too. So we're hiring as well, which is also pretty cool. So I don't do this work alone. I have a very inspiring team. And then I could put on a bunch more faces of our extended community that helps us get this work done. So a huge thank you. There's my email address. These are most of our partners that support our work. And I am happy to take questions, and feel free to, reach out anytime. So thank you.
Thank you. Hey, John, you want to come back in? No. Are there questions?
Oh, my
Oh,
mute
go ahead,
off now?
John.
Yeah. I had a question. I was wondering if Dr. Cannon's aware of any processes that can be integrated into waste streams that would increase the biodegradability of solvents. I mean, we hear about photochemistry all the time. We try to avoid the degradation of our materials, but is there a way we can harness that in our waste streams?
That's a great point. I don't know specifics. I know that there's a couple green chemistry. If you're not familiar with the Green Chemistry Challenge Awards, that's an award given out by the EPA and the American Chemical Society Green Chemistry Institute. And they just gave them out last week at Climate Week in New York City, and they highlight different companies and academic researchers that are doing work in this space. And I know there's a couple that are focused on that. Like one was a researcher at Carnegie Mellon, Terry Collins, who has some pretty cool chemistry to help break down some things that are harder to break down in our water systems. Things like you can imagine some of the very persistent chemicals that we have, like PFAS and some of those things that can help break down using some really creative catalysts. And they're more benign catalysts. They're iron-based. So there's some really cool technologies. That's one that comes to mind. I'm sure there are others, but those presidential, they used to be Presidential Green Chemistry Challenge Awards. They're now non-presidential. It's just Green Chemistry Challenge Awards. Those have been given out since about 1996. And there's some really great case studies in there of companies and innovative technologies. So that's another great place to look for if you're looking for something specific that might demonstrate something like what you were just talking about, breaking, things down in the water systems. That could be one place to look. But that was Terry Collins from Carnegie Mellon, and his catalyst was called TAML. And I know I will not remember the acronym at the moment, but it's pretty cool. There's some case studies out there. We might have some in our curriculum, I wonder. I could have a look.
Oh, good. Thanks.
So I have a question. So you put together a guide for like organic chemistry labs. Are you planning on putting together, or do you already have some collection or regarding biocatalyst?
Biocatalyst. That's a good question. So we had an inorganic working group. I don't know if they've been looking, because I think they've been looking at more earth abundant metals and things like that we can substitute in. I don't know about the, but there are some resources. So the other thing that we have, I'm going to stop my sharing for a second. The other thing that we have is a full course curriculum we have an Intro to Green Chemistry course. It's all open access materials, and I think there could be something in biocatalysis in there because it's framed around, and I'll just put the link here. It is also on the GCTLC. I feel like I'm like a broken record with that thing. But there's some good resources. We did it with Yale Center for Green Chemistry and UNIDO, and it's a full set of course materials. So if you're looking for a particular topic, could also be in here. So this is the course, and you'll find that the lecture. So this is if you wanted to teach a full course on an Intro to Green Chemistry, it's got more than 36 hours of content all in here. But you can also take the one. So if you could go down to the one that says catalysis, because they're framed around the 12 principles. I believe that there's information in there about some biocatalysis. So you can also just look at, hone in on one. Like there's a really great resource in here for analytical, like how we might think about bringing in green chemistry to our analytical course, which is also a good one.
Yeah, because I know that in the literature, of course, there is a lot of information about using different enzymes and all of that. Many of them are commercially available. But when I say biocatalysts, I'm also including just different fruit juices, natural juices. And there are papers out there that, for example, replaces hydrochloric acid in a process with lemon juice, lime juice, tamarind, a lot of different stuff. So I think that might be a good thing to also try to compile. Yeah.
Absolutely. I think that's I love how you're thinking.
Well, we've been talking. Yeah, I guess John was last year, you were this year. I want to have almost every year someone that's focused on green chemistry in our seminar program. So we'll be talking to you again to suggest speakers as well.
That would be wonderful. Happy to make some suggestions. And anytime, happy to connect.
All right, other questions?
Yes, I was wondering, I don't know if you mentioned this and I missed it, but so when we're looking at like Greek chemistry, are we also looking for molecules that are harmful? Or are we just looking at ways to improve? Like, how do we tell which molecules are bad to start out with?
So his question has to do with basically the toxicology side of things, right? The product, is that going to be toxic? Are the starting materials toxic? And I believe you showed us a book that you guys have put out.
Yeah, that's also another. Did you get that right? Yeah, that's also another collection of resources. So the toxicology, I will also put a link in here. It's called Toxicology for Chemists curriculum. And you can find all kinds of things on here for starting from like how to think about hazard information. Like how do you find good hazard data around what makes a molecule toxic? We have some great modules around that, to being able to do more of like the predictive toxicology. So how do you think about and look at structures, and are there mechanisms for understanding things like, is it going to be a carcinogen? Is it going to be persistent? All the different toxicology endpoints. There's like, in some of these chemical hazard assessment tools and things, there's 21 different hazards assessments, or endpoints that we're looking at. So it's not just one thing, right? It could be something as mild as like a skin irritant to something like a carcinogen or an endocrine disruptor. And there's a huge spectrum. And so there's all of that. I would say most of that are in these modules. There's a module on reaction mechanisms. So understanding when you're learning about SN1, SN2, when you're learning about, all of these different reaction mechanisms, hey, they're actually ones that are common in our body and like that might lead to some negative impacts. So if we know that something's going to be a Michael acceptor or something, with that, hey, that's going to cause more damage in our systems, right? In humans and animals. So there's a lot of that in there, and I'm trying to think of, and also like structure, function, activity, those sort of activity relationships. There's a lot about that, like understanding how, the more we understand how structures impact toxicity and impacts, the better. So yeah, there's a lot in there. I don't even know if I answered your question, but there's a lot of information in there. Yeah.
So it seems like the ideas that you guys are, putting out there are being accepted across academic and industry. Have you been getting full acceptance? Are you getting pushback? You showed some statistics that are pretty.
Yeah, what we're finding, so there's good evidence that this is being more broadly accepted from things like the ACS new guidelines that, that they're looking for including these things also in curriculum. Industry, some of our main partners are MilliporeSigma, Dow, some of the big companies, the Target actually funded the development, like the store Target developed or help support the development of this toxicology for chemists curriculum, because they're really interested in having better products in their stores. And they saw this as a pathway for that, so we work with chemical companies all the time that are looking for chemical companies, brands, even Apple, that are looking for better ways and better, science, the development of better products and chemical products. So yeah, there's pretty good acceptance. Yeah.
Right, sounds good. We probably need to wrap up now, but you and I will be in touch for sure.
Yes.
And thanks again for coming on and accepting our invitation and increasing our knowledge about, environmental and green chemical knowledge.
Yes.
Thank you so much.
Thank you, Desmond, and thank you, everyone. Feel free to reach out anytime.
All
Thanks.
right.
Okay.
Take care.
All right.
Thank you.
Thank you.
All right. Bye-bye. Yeah,